We have seen how to approximate a function with a line and with a second degree polynomial. But now suppose that we want to approximate it with a polynomial of nth degree, c0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed plus everything thereafter until we get to c sub n x minus a to the nth degree. Our job is going to be to find the c sub 1 through c sub 0 through c sub n that will perfectly fit our function f of x. And for that, we would need the conditions that our polynomial evaluated at a is equal to f of a. The derivative of a polynomial at a is equal to the derivative of my function at a. Second derivative of my polynomial at a is equal to the second derivative of my function at a, and so on and so forth until we get to the condition that the nth derivative of my polynomial at a is equal to the nth derivative of my function at a. If we look at these conditions and see what values of c0, c1, all the way through c sub n satisfy it, we come to the conclusion that if you want to find your c sub k, you can do so by taking the kth derivative of your function, evaluating at a, and then dividing it by k factorial. In this case, the factorial is a computation that takes your number and multiplies it and all the numbers before it until you get down to 1. For example, 4 factorial is equal to 4 times 3 times 2 times 1. And just as a note, 0 factorial, by definition, you can assume that it's equal to 1. So if we want to find this polynomial, we can easily find the coefficients using this formula. So our polynomial p of x will look something like f of a plus f prime of a times x minus a plus f double prime of a divided by 2 factorial times x minus x minus a squared plus f differentiated 3 times evaluated at a divided by 3 factorial times x minus a to the 3rd power plus everything thereafter until you get to the nth derivative of f at a divided by n factorial times x minus a to the nth power. This is known as the nth degree Taylor polynomial of f of x centered at a. Let's use this to find the 3rd degree Taylor polynomial of the function ln of x centered at a equal to 1. So find the 3rd degree Taylor polynomial of f of x centered at a equal to 1. So I'll start taking derivatives of my function. Here's f of x equal to natural log of x. Its first derivative is simply 1 over x. its second derivative is negative 1 over x squared, and its third derivative is 2 over x to the third power. I'll evaluate these guys at 1. So f of 1 is the natural log of 1, which is 0. F prime at 1 is just 1. F double prime at 1 is negative 1. And f triple prime at 1 is equal to 2. So C0 would be f of 1 over 0 factorial, which is 0 over 1, which is simply 0. C1 is equal to f prime at 1 divided by 1 factorial, which is 1 over 1, which is 1. C2, which is f double prime at 1 divided by 2 factorial, is negative 1 over 2. And C3 is equal to f triple prime at 1 divided by 3 factorial, which is equal to 2 divided by 3 factorial, which is 3 times 2 times 1, which is 6. And this simplifies to 1/3. So our third degree Taylor polynomial would be 0 plus 1 x minus 1 to the first power minus 1/2 x minus 1 to the second power plus 1/3 x minus 1 to the third power. Let's take a look and see if this is a good approximation to my natural log function close to x is equal to 1. So let me turn off the previous functions here. Here is the graph of my natural log function. And here is my polynomial. And notice that my polynomial in red is a good approximation to my natural log function for values of x that are close to 1. And again, if you go further out to the left or further out to the right, you do end up getting less accuracy, but close to 1, you do have some really nice approximations.